Today we're going to be discussing the progression of the atomic model and really how we gained our understanding of what we now think an atom looks, acts, and really is just like inside. Now, in order to start this discussion, you might recall that we actually have to go back thousands of years. And when we're looking thousands of years ago, we're looking at two philosophers, Democritus and Aristotle. And remember, Democritus is the one who originally came up with the idea of the atom. He thought of something that would be small, indestructible, and really uncuttable. That's what atomos means. And he thought that all matter was made of these itty-bitty, teeny-tiny particles. Aristotle didn't believe in atoms. Aristotle believed in a model that was continuously divisible. So really, you could always get smaller and smaller and smaller and smaller and smaller. You never got to a particle that was uncuttable. He was also the one that believed in the four elements. But remember, when we're talking elements there, we're not talking hydrogen, oxygen, nitrogen. We're talking earth, wind, fire, and water. And for thousands of years, everyone believed Aristotle, even though Democritus was actually closer to what we now believe. But because Aristotle had the backing of the church, Democritus, well, he was pretty much out of luck. Now, after a few thousand years, really 2,000 years, we start getting into this age where scientific discovery is really becoming key. And at that point, if you remember, we're looking at John Dalton. And Dalton is the guy who first wrote our atomic theory. And we're going to make that a capital T in theory, because remember, in science, a theory is more than just an idea. It's more than what Democritus or Aristotle had. It's something that has a lot of evidence to back it up. And what we're going to do today is we're going to go from Dalton's idea and Dalton's atomic theory all the way to pretty much our modern understanding of what an atom looks like and acts like. And we're just going to look at the progression of how we got where we are. So let's start with Dalton. Remember, Dalton had his atomic theory, and Dalton's atomic theory had the four postulates. So all matter is composed of extremely small, indestructible particles called atoms. Now we say, well, you can actually break an atom, you just have to do a nuclear reaction. Atoms of the same element are identical in terms of size, mass, and other properties. Well, now we're really just talking atomic number and number of protons, because we know that sometimes you have something called an isotope that might have a different mass, or an ion, which might even have a different size. Atoms of other elements are different from atoms of the same element based on atomic number and protons. Atoms of different elements can combine with one another in simple whole number ratios to form a chemical compound. And remember, when we combine atoms, what we're forming is called a molecule. And chemical reactions can be described in terms of separating, combining, or rearranging atoms, but atoms cannot change into an atom of a different element as a result of a chemical reaction. So basically, what's there in the beginning is there in the end. And when we're looking at Dalton's atomic theory, and we're thinking about the evidence that led us to this understanding, we have three early laws that we're going to be looking at. We have our law of conservation of mass, that basically just tells us that whatever mass we start with, those are called our reactants, have to be the same as the mass of our product, the things we end with. We have our law of definite proportions that tell us that if you have a compound and you have multiple samples of the same compound, then the mass proportions have to be the same in every sample. So if it's a 1:2 ratio in the first sample, every sample is going to have a 1:2 mass ratio of the elements. If it doesn't have a 1:2 mass ratio, then it must be a different compound, and that's where the law of multiple proportions kicks in. It just compares how much of the mass of one element reacts with the same, or 1 gram, of the other element. And when you compare all of the different compounds that have the same two elements, then you're going to get small whole number ratios in the end for those. These three laws are what we're going to actually use as our evidence for Dalton's atomic model. Keep in mind, models are more than just diagrams because they also should include a causal mechanism. And the causal mechanism that we're going to be looking at is going to be coming from things like our evidence of our laws or the evidence from our experiments. So in order to come up with the laws, the scientists that were working around the same time as Dalton were doing experiments on air. They were doing experiments on gas state of matter. So I'm going to list that as the type of experiment that was done. And then for Dalton's atomic theory and Dalton's atomic model, I'm going to say that based on these gas experiments, we had certain evidence. And the evidence that I'm going to list for Dalton are those three laws that we just reviewed. But when I combine these three laws that came about once we realized that things like gases also exist and have a mass and are part of matter, then the model that Dalton actually came up with just looked like a solid sphere of neutral matter. And this solid ball, this solid sphere, Dalton called the billiard ball model. Remember billiard ball? That's just like a pool table, pool ball. So billiard ball is just a solid sphere, neutral matter. Now, obviously, at this point, we know a lot more about an atom than just the fact that it's like a round ball. And in order to get from where we started with our model to where we currently are with our quantum mechanical model, we had to have several scientists and several different models that really arose from different evidence from experimentation. And these ideas, the scientist, the experiment, the evidence, and the model, this is what you're responsible for remembering. Within a couple hundred years, we made really great progress with our understanding. And actually, the first few steps were really within a decade or so. So we went from Dalton's atomic theory to our next model, which is based on experimentation from an apparatus that kind of looks like this. This is known as a cathode ray tube. And the cathode ray tube was not created to try to test these ideas of atomic theories and atomic models. The cathode ray tube was really just a cool piece of technology that was new back in that day. And the scientist that really kind of put things together is J.J. Thomson. And Thomson is our next scientist that you are responsible for. Now, some sources are going to have a P in his name, Thompson, some don't. I usually don't put it in there, but it really makes no difference to me. What you need to remember is that Thomson was experimenting with a cathode ray tube. And the cathode ray tube looks like this, where you have your cathode and your anode, kind of like in a battery, and it pulls an electrical charge across and through a small little hole in the end. That little piece of electricity that is getting pulled across and shot out generally goes straight across in a straight line until it hits something that could deflect it. And what Thomson was using was actually a screen where he could see where this electric piece kind of hit. Now, what Thomson realized is because of how he had this set up and what he was using to actually get this beam of light or this electricity, he realized that whatever this cathode ray was made up of actually had to be part of the atoms that Dalton was referring to. And because what Thomson did is he actually put charged plates above and below this tube. And when he did that, the beam actually bent. It didn't go straight, it bent toward the positive side. Now, based on our understanding of charges and the fact that opposites attract and likes repel, the fact that this bent toward the positive, or you could think of it as away from the negative, told Thomson that whatever this was, whatever this ray was made of, whatever this electrical bit was, had to have a charge. This ray had to be negatively charged in order to be attracted to the positive plate. And when he looked at the model that we started with Dalton's billiard ball model, he realized that it couldn't be quite complete. So Thomson was doing the cathode ray tube, or the cathode ray tube experiment, and he realized that the ray bent towards the positive, or you could think of it as away from the negative, which means it actually has a negative charge. And the fact that we now know that a piece of our matter has a negative charge means we need to adjust our model. So he didn't throw away the model. He didn't start all over. He actually kept the idea of there being a sphere. But on the sphere, he is now going to add little pieces that have negative charges. And these little negative charges, we now know as electrons, get added to this plum pudding model. Plum pudding is a British dessert. You can also think of it as the chocolate chip cookie dough model. We don't want a chocolate chip cookie model because we don't want it to be flat. We want this to still be a sphere, but a chocolate chip cookie dough or plum pudding model would suffice. Now, the only other thing that we need to point out is that when we had the billiard ball model, it was a solid sphere of neutral matter. But now, because we have negative particles embedded in there, but we know that the entire atom overall isn't negative, this solid matter is now thought to have been positively charged. And again, that's really just to balance out the negative charge particles from the rest of it. So, Dalton, gas experiments, evidence was our early laws, and he came up with the billiard ball model, which was a solid sphere of neutral matter. After experimenting with the cathode ray tube, Thomson realized that the only way the ray would bend toward a positive plate is if that ray was negative. So now he needs to have some negative particles. And since we have negative particles but an overall neutral charge, he made our solid sphere positive instead of neutral. So first two, billiard, plum pudding. In order to get from one to the next, we just needed some evidence. The next experiment that we were looking at is actually the oil drop experiment. And this was Millikan who was doing this experiment. And basically he used an atomizer, so just like a little perfume bottle, to spray oil into a chamber, which would then pass through, and actually it would get some x-rays shot at it, which would give each little oil drop a charge. And as they went through then, they fell through a charged field. And what Millikan was actually able to do is kind of cool. He adjusted the amount of charge in this field and made these little drops of oil stop falling. So by adjusting the field, he was able to get the oil drops to really levitate, stop moving, and then actually start moving back up. And because he was able to figure out the amount of charge required to get each oil drop to do that, he was actually able to determine the charge and the mass of these little particles, these negatively charged electrons. But because his experiment, this is Millikan's experiment didn't actually disprove anything about Thomson's model, it just kind of added to our understanding, Millikan doesn't actually get a new model. So in order to get our next model, we actually need to talk about Rutherford. And Rutherford's experiment, what he was doing, is known as the gold foil experiment. So it looks kind of like this. We have an alpha particle emitter. Alpha particles are radioactive particles that go through a slit and then get shot through a really thin piece of gold foil, like aluminum foil, but made out of gold. Based on what Thomson thought the model looked like, remember our plum pudding model? Rutherford said that all of these particles should pretty much shoot straight through. So if you think about the particles kind of shooting through this atom, which was Thomson's model, it would either go through an area here or here or here, but because all of this charge, this positive and negative, was fairly even distributed, it's not going to be repelled. It's not going to deflect any which way. Now, when Rutherford actually did his experiment, most of them did actually go straight through, but occasionally one would get deflected. It would kind of bend, which Rutherford said, okay, well, maybe that's just it's kind of hitting where there weren't many of these electrons, many of these charges. And so maybe it gets deflected a little, positive alpha particle, positive matter, it could happen. But then what he saw was occasionally, like we're talking 1 every 10,000 times, these alpha particles would actually shoot straight back and hit the backside of our screen. And that was incredibly unexpected. Rutherford is actually quoted as having an analogy where he said that this would be like shooting a cannonball at a piece of tissue paper. You would expect the cannonball to go straight through. But his results were so surprising that he said it would be like if you shot that cannonball at the tissue paper and the cannonball actually ricocheted back and hit you. There is absolutely no reason that any of them should have bounced back if Thomson's model was correct. So Rutherford said it can't be correct. We need to create a new model. And the model that Rutherford created is called our nuclear model because it is the first one to include a nucleus. So the idea is that usually alpha particles go straight through atoms in the gold foil because usually they're just going through this empty space. And there's still electrons around here they might interact with a little bit, and you might get a little bit of bending. But every once in a while, when it comes straight back at you, that would be like the alpha particle actually hitting the nucleus dead center and ricocheting back. So again, the person that we're now looking at is Ernest Rutherford. The experiment that he was doing is the gold foil experiment. His evidence was that occasionally, not very often, the positive alpha particles bounced back. And based on the fact that it was only very occasionally, he knew that that positive area they were bouncing back off of had to be really, really teeny tiny. In fact, if you think about the atom, and you think about the entire volume of the atom being as big as our stadium, not just the football field, but the entire stadium, then the nucleus of the atom would be about the size of a dime. And that dime, you could think of it just kind of sitting on the 50-yard line. If you start throwing anything across the stadium, the chance that it's going to actually come into the area close to where that dime is incredibly small. But if it does, that's when we would get our particles to bounce straight back. Based on the evidence from the experiment, Rutherford made our new model, and basically what he did is he took the plum pudding model, which remember had those negative particles in the solid sphere, and he took all of that positive solid sphere and shrunk it down to the very center. So we have our positive nucleus, we have our negative particles, and the issue is that when you separate a positive nucleus with negative particles, you're really left with nothing between them. This is just empty space, which means that according to Rutherford's nuclear model, the majority of an atom's volume is nothing. It's empty space. So even like the atoms that are making up this whiteboard right here, the majority of these atoms are nothing. They're empty. In the very, very teeny tiny center, we have our positive nucleus. And outside the nucleus, we have these electrons that are traveling in the region called the electron cloud. but the majority of the actual atom is empty space. It's nothing. It's not air, it's nothing. And that's actually the problem with Rutherford's model, because Rutherford was presenting this model and he couldn't explain to the people, the scientists that he was presenting to, if we have a positive and we have these negatives and there's nothing separating them, what's to stop these electrons from actually spiraling right into the nucleus? We know opposites attract, so why wouldn't these negatives go into the center? And Rutherford couldn't really answer that question. And because he couldn't answer the question, he was actually ready to completely get rid of this model. He's like, oh, I guess I was wrong. But luckily for Rutherford, he had a student at that time known as Bohr. And Bohr's model, Bohr's planetary model, is actually the model of the atom that most kids think of when we talk about atoms. And in order to really understand Bohr's model, we do have to have an understanding of something called wave-particle duality and really some photoelectric type things and even an electromagnetic spectrum. But we're not going to get into all that today. All we're concerned about today is the actual experiments that Bohr was doing. And the experiment that Bohr was doing involved something called an emission spectra of hydrogen. And really, what it comes down to is kind of like passing light through a prism. We use these things called spectroscopes, which you'll actually have an opportunity to see in class one day. But a spectroscope is kind of like a prism in that it separates light out. So if we think about visible light, visible white light coming from the outside, you're going to get what we call a continuous spectrum. And that's like this. You see it's all kind of blurred together. We have the whole rainbow, red, orange, yellow, green, blue, and violet. This continuous spectra is a blur. But when Bohr ran the emission spectra of hydrogen, he didn't get a blur. So the idea that Bohr had, which kind of saves Rutherford's model, is that we have our nucleus and we have our electrons, but the electrons have to be within certain levels. These are called energy levels, sometimes also called orbits back then. And Bohr's idea is that you have electrons within these certain regions, but if you excite the electrons, if you pass electricity through them or put them in a fire, you can actually make the electrons jump from a lower region, called a ground state, up to a higher region, called an excited state. Now the excited state's really unstable, so it immediately falls back down to the ground state. And as the electrons are making these transitions, and sometimes they transition over one ring, sometimes they transition over a bunch of rings, they're going to absorb and release energy. So again, we start at the ground state, we add energy, the electron absorbs it, it jumps to an excited state, which is really unstable, which means it has to fall back down. As it falls back down, it has to release that energy as it goes back from the excited to the ground state. What Bohr realized is that if you use these spectroscopes, you can actually see the different colors that are associated with how far these electrons fell. And if Rutherford's model had been correct and the electrons were free to travel anywhere they wanted to, then we would get a continuous spectra because the lights would all be smooshed together. But every time Bohr ran the emission spectra for hydrogen, he actually just saw 4 distinct lines. Now, iron is shown here in this example, and you'll see that there are lots and lots of lines for iron, but you'll notice that it's not a continuous blur. So even when we get to something like iron, which we actually have to use our new model, the quantum mechanical model, that's our evidence for that one, it's still not going to let the electrons go wherever they want. They have to stay in distinct regions, and the distinct regions are associated with the energy that it takes to fall from one ring back to another. So if the electron only falls a little bit, it releases a wavelength of light with a big wavelength, that's like red. If it falls more regions, then it's going to release a wavelength of light that has a small wavelength, and that's a lot more energy because it's going through more energy levels, and that would be on the blue where the violet end. The fact that Bohr always saw the line spectra and never the continuous spectra told him that the issue with Rutherford's model is that the electrons can't go wherever they wanted. Instead, they had to stay on the rings. And this is now known as our planetary model. Planetary model still has our nucleus in the middle. It still has the electrons outside the nucleus. It even still has the empty space between the rings. But these actual energy levels, or orbits, are the big difference. And remember, the evidence for that is that we had the line spectra, not the continuous spectra. So Bohr knew that the electrons could only be in certain regions associated with these lines every time they fell between the rings, not anywhere they wanted to go. And that gets us all the way to Bohr. So again, throughout what we've discussed today, we've gone from Dalton to Thomson we threw in Millikan, even though he didn't get a new model. We had Rutherford. And then we had Bohr. And that's almost a complete, really, trip through our atomic models. The only one that's missing is the one that we'll spend a little bit more time in during the next few lessons. And that's our electron cloud or quantum mechanical model. And the electron cloud quantum mechanical model, you don't need to know a lot about it right now. Really, you just kind of need to know how it's different from Bohr's planetary model. So it still has a nucleus, and it still actually even has regions where electrons have to be. But now instead of those regions all being circles, we're going to get some other shapes. So we'll have some things that look like figure eights. We'll have some things that even look like four-leaf clovers. And we'll have some things that look like multi-petaled flowers. And I'm guessing that you would notice that as we fill more and more electrons into this electron cloud or quantum mechanical model, this gets really ugly. It's really hard to see anything in it. And that's why in our next lesson, we're going to actually have to learn how else we can represent this model other than just drawing it out. After today's lesson, you should be able to describe from Democritus all the way through Bohr. If you have any questions or need any help, absolutely let me know.